Hello, my name is Patrick Rowan, and this is my lab report on circuits. So the purpose of this experiment is to gain a better understanding of circuit behavior and to use our knowledge of circuits to make a prediction as to how it'll behave and function based off of its composition. Additionally, we intend to observe a real-life scenario where the node and loop rule would apply and verify them by our observations. So some results that we gained were that the loop rule was proven to be true, as the sum of all the changes in potential, specifically in the battery and the resistor, summed up to be equal to 0. And also our slope, of which will be discussed later on, which is equal to a -1 over RC, was found to be negative 0.167. So some fundamental physics principles to be aware of, or Ohm's law, which is that the potential is equal to the current times resistance. Kirchhoff's loop rule, which states that the sum of all the voltage drops from the loop are equal to 0. Kirchhoff's node rule, which states that currents entering the node equals current leaving the node. And then just a general understanding of resistor-capacitor circuits and how resistors and capacitors behave. So in experiment 1, we had a circuit comprised of 2 batteries, which summed up to be equal to 3 volts, as well as 2 ammeters, one on either side of these 2 resistors, one being 47 ohms and the other being 100 ohms. The system was the circuit itself, surroundings were the table, the lab room, and everything else surrounding us, besides the circuit. And then initial conditions were that before being plugged in, there is no current running through the wire, so the ammeters read all zeros. And then by using charge conservation, we determined that the I values should be approximately 0.02 amps. So for this experiment, and unfortunately this picture does not show the eventual values we obtained for the current at the ammeters, but we eventually did pick up that the current was approximately equal to 0.020 amps like we calculated. Also when the ammeter was reversed, a negative value was read, so negative 0.020 amps. And then by replacing the ammeter with a voltmeter, it led to values of 3 volts being displayed on the voltmeter and 0 being displayed on the ammeter. We think this is because the voltmeter has very high resistance and was not allowing any current to properly flow through the ammeter. So here we have our potential difference chart showing how it's 3 volts as it passes through the battery, but then the values from C to D, which is from the first resistor, drops it by 0.090 volts, and then from E to F drops it from 2.1 volts, which leads to the potential being equal to 0, which again satisfies the loop rule. So the second part of our experiment, which involved a circuit which was composed of batteries, capacitor, and light bulb. The system was the circuit itself again, surroundings were the table, lab room, etc. And then the initial conditions were that when the circuit was open, the current is equal to 0 amps, and the capacitor has no charge. So observations we made were that when, after being connected to the battery, the bulb at first shone brightly and then dimmed with time. And then afterwards, when the circuit was reformed without the battery, after the capacitor was charged, the bulb again initially shone bright and then dimmed with time. So RC is a time constant of the circuit, the time which the voltage difference has dropped to 1 over E of its original value. That can be found using the equation shown on the right, relating the natural logarithm, changing potential, and then negative T over RC. So plugging in our values for R and C and T is equal to 1, we are able to find that the slope was equal to negative 0.167. So assumptions we made were that batteries were fresh and fully charged. Multimeters used were reliable. No resistance was in the wires or ammeters or whatever, and that there was no human error in how the circuit was set up, and the multimeters were used. So the what if questions, and if we basically with the first question, we realized that the virtual and the real-life ammeters behave differently because the virtual ammeter and the wires have 0 resistance, while with the real circuit, the ammeters and wires have a very small but present resistance that affects the final charge. Again, it was pretty negligible in our results, but overall there was a slight difference. And then the second what-if question was why, which was why the measured time is different from predicted time, we ended up getting a significantly longer time measured than in the real life over the virtual model. This is because the resistance associated with the capacitor and the battery is not accounted for in the virtual model. So, thank you for your time.